Well, hello, fifth grade. Welcome to the end of a working week. Everybody's working for the weekend. So I thought on this phrase day, we could do an investigation. Investigation 10, cubes. Yeah, let's do it. Might as well jump right in. So it's a little bit ahead of when our investigations usually would drop, but that's just fine. And on investigations, we don't give any official homework. So this is just, obviously you got to take notes. And I want you to think about these ideas. But just something to kind of get in your brain that we will continue to work with, especially as we move forward into junior high. So what is a cube? Well, a cube is a type of rectangular prism. We're going to practice drawing one right now. So this is what I want you to do. I want you to draw a square. Then I want you to extend off of those three right side vertices. So 1, 2, 3. Make sure that those extendos are kind of same size and they're parallel. And then we're going to connect those, boop and boop. And you've drawn a cube. If I know that something is a cube, that just doesn't mean that it's kind of boxy. I mean, cubes are very specific in mathematics. So one thing I could mark to prove that this is a cube is this. Boop, 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 boop. And those 4 boops tell me, those little tick marks tell me that those sides are congruent. In order for it to be a cube, I would need a little bit more information. But let's say that side length was 1 inch. Therefore, if this is a cube, which would also mean that's a boop, and 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 booping everywhere around, right? Like every single side length every single edge is exactly 1 inch, and that would be classified as a cube. Now, another way we could draw a cube is if it looked like this. So model with me now. We'll draw the square. Then I'm going to draw it a square, same size, just kind of in the corner of it, like so, like halfway in it. You see that? So I'll take it back. Ready? Boop, 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 right? Then I connect. Now this would be like if I was Superman and I could see through walls. This is kind of what I'd see, right? Is this a cube? Well, it would kind of depend on the markings, but that is another way that we might see a cube drawn. So this investigation has us looking at a few ideas. Here's the first idea that we're really going to look at, which is having to do with volume. Now, volume is something that we do with 3-dimensional objects, such as a cube. And volume would be like if I was going to fill those little cubes with, let's say, sand or milk or water. So we do have a formula for volume. And that formula for a volume of a cube is V for volume equals S cubed. That S represents side length. So if I was to take a cube like this, boom, 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 and I was to name this side length as 4 feet, then in order to figure out its volume, like again, if I was like a hole in the top that I was going to fill up with apple juice or something like that, how much apple juice would it be? That's a question of volume. So I would say, okay, V is equal to, and I'd open up my set of parentheses, wrap this in parentheses, and I'd cube that, right? So then I'd say, okay, so V is equal to, now 4 cubed, or 4 to the power of 3, we should know means 4 times 4 times 4. Now, 4 times 4, we should know is a basic fact. That's 16. 16 times 4, probably not a basic fact. Some of us might have it in our brain. If we don't know, we can figure it out, right? 16 times 4, 6 times 4 is 24, carry the 2, 64. Therefore, the volume is 64, but then we have to remember this feet to the 3rd power, or feet cubed, which we could just write as feet cubed. As you know, we've talked about this before. There is another way to answer this. It's more what you might hear at the hardware store, which would be something like, I need, Mr. Hardware Store Man, I need 64 cubic feet of lemonade because I got to fill this box, which you might like a little strange. Because you're like, wait a second, wouldn't you tell them quarts or gallons? Yeah, we could, but we've got to kind of deal with that later. Quite simply, the volume of this cube is 64 feet cubed or 64 cubic feet. Yeah. Here's another idea we got to get into. So let's go ahead and draw this up. The big question is, you see the drawing on the left is what we would call a 1-inch cube. It is a cube where all of my edges are exactly 1 inch. And the question is, how many 1-inch cubes would fit in a 10-inch cube? And that's the picture you see on the right. So that picture on the right is also a cube, except for in this time, their edges are 10 inches long. And again, what's your guess? So some of us might guess 10, but go, well, maybe that's not enough. Maybe it's 100. Yeah, this is possible. Could it be more? Well, if we go back to our volume idea, and we determine the volume of this 10-inch cube, wouldn't that be side cubed, right? So the volume is equal to, and opening up my parentheses, or closing in parentheses, would be 10 inches raised to the third power. Now, we do know that that means 10 cubed means 10 times 10 times 10. And you can go ahead and work that out. However, there's kind of a little trick with tens and exponents is you just really have to think about the 3, the exponent, and the 0. And notice that what you're going to end up with is a 1 with, guess how many zeros? Yeah, 3 zeros. 1, 2, 3. So the volume of my 10-inch cube is 1,000 cubic inches. Therefore, how many 1-inch cubes do you think I could fit in the 10-inch cube? Well, if you said 10, you were a little off. If you said 100, you were a little off too. But if you said 1,000 1-inch cubes, you would be right. Yeah, kind of a lot, huh? It's because it's exponential. It goes crazy exponential-wise. Hey, here's another idea I want to explore. There's something called nets. And nets are 2-dimensional views of a 3-dimensional object. This is, we're going to draw a cube. This one we're going to draw a little bit different though. So I want you to draw a square like you see. We're going to come off the edges like before. But here's a cube that I can't see through. Now, if I really was going to see through it, or the way they usually show me seeing through it is not with solid lines, but they're dotted lines. So this is what I want you to do. You're going to draw a dotted line like so, coming down to the kind of make a square. Then dotted line it this way. There's your square in the back. You see it? And then dotted line it here. And there's your square on the bottom. And you draw on a pretty good looking cube where I can see through it. But the things I can see through, they're shown in a dotted sort of line, right? Now, this is not a net. This is a 3-dimensional view of a 3-dimensional object. A net would look more like this. So a net for a cube could look like this. And technically, those aren't really solid lines in the middle. We'll talk about that in a moment, but this would be a potential net. And the idea is you would cut around the shape and you'd fold on all of those lines. Now, what I want you to see is that if I was going to look at my original shape, the one on the left, this is what we'd probably call the front. Well, for this net that you see to the right, the 2-dimensional view, this would be my front. And then if I think about my top, this over here would be my top. And then if you think about my bottom, right here, there's my bottom. Well, this would be my bottom over here. Now then I also say I have a front, I have a top, I have a bottom. I also have what we might call the sides. So this thing on the end is my right side. This one's my kind of left side. And there's my back side. You see my back side there? Yeah. And so that's what these would be. Right? Boom, boom, boom. But technically, when we look at nets, they don't have those solid lines in the middle. They actually have like a dash. Dash, 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 dash. Dash, 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 dash. Not on the outside, just on the inside. And that dash, 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 those are our fold lines. So what I was saying is like, if I gave you a net, like let's say on like kind of cardboard sort of paper, what you could do is you would cut around the outside like a boop, 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 cut, 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 cut. Then you'd fold along all the little fold lines. And if you did that with the shape on the right, guess what you'd end up with? Yeah, you know, a cube. Hey, here's something to look at. Here are 3 nets. Which one would form a cube? Or which ones would form a cube? So if we look at the one on the left, if you can kind of visualize folding up and folding and folding and folding, would you say the one on the left is a cube? Yeah, good job. You'd be right. That one is a cube. Well, this one on the right, slightly different, but could it? If I cut, and I folded, would it form a cube? What do you think? Yay or nay? You say yay? I say yay. Well, then maybe they're all cubes. I don't know. Let's look at the one on the bottom. So again, cut, fold. would this fold into a cube? You say what? You say no? Yeah, no would be right. The reason why is like it's kind of right here. Like these guys, as we like fold it in, wouldn't they kind of like they'd fold onto each other, and we'd have this like kind of opening over here, like a space. And cubes don't have space like that. All right, last idea. I promise. Remember, there's no homework. Surface area. So surface area is, again, something we think about with three-dimensional objects. When we look at a cube, boop, 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 and we look at the inner of that cube, let's say this one was 5 centimeter, it's a 5 centimeter cube. Now, surface area is figuring out the area of the faces. So there's one face, here's another face, here's another face. In fact, all cubes and all rectangular prisms have precisely what we call 6 faces. Now, if we were just going to consider any old square, we know that the formula for area of a square is A equals S squared. But if you think about that, how many squares are in a cube? How many faces? Well, like I said, there's 6 faces. So if I'm thinking about surface area, I would say the surface area of a cube, its formula will always be S squared. That's just one face. How many faces I need? Boom, 6. 6S squared. And how would I do it? Well, I would just plug in SA is equal to 6, open up my parentheses, put my 5 centimeters in, and I'd square it. Now remember, you have to follow the order of operations. So I know I'm going to do my exponents, PEMDAS. Please excuse my dear Aunt Sally. So parentheses, then exponents. So say SA is equals 6, and then I have to figure out, well, what is 5 centimeters to the second power? Well, 5 squared is 25, and centimeters to the second power is centimeters squared. Now I can multiply that 6 times 25 and say that the surface area, and I should be able to deal with my 25s, would be 150 centimeters squared. And I can box that up. And you can go back here, or I can go back here and say, hey, 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 it's Friday. And you don't have any homework. So I hope you enjoyed the investigation. Cubes are kind of cool. You know, when I was a kid, the worst part of going out to dinner with adults is they'd always talk at the end. But the cool thing is, even after we were having dinner, they'd bring out coffee and they'd put in front of me, like in front of the adults really, but like a plate of sugar cubes that they would drop into their coffee. But man, I ate sugar cubes like there was no tomorrow. Cubes. 6 faces. Pretty cool. Hope you're well. Bye.